Alfredo Iusem, and he's going to talk about the recent results in asymptotic analysis with applications in optimization theory. So the floor is yours.
Okay. Thank you very much, Maicon. Now, before I start with the specifics of the topic, I want to thank all of you for coming. I'm quite moved by your presence. It's been sort of an emotional week for me. And I thank all of you and also those who already left because there are compromises. I'm very happy. And it's sort of a, let's say, a very important point in my career. Second thing, I want to thank very specially 3 persons who were absolutely essential for this meeting and for what I think I could call its success. And first, Fernanda Haupt, who has been working tirelessly. She has been an excellent collaborator, and most of the preparation of this meeting has been done through her and also through the people working at the events department of IMPA, particularly Sueli Mayato and Leticia, who have been and still today, and also next week, because there are a lot of accounts to be settled and all that, will work very, very hard. They have a lot of work at IMPA. We have many meetings every year, so as soon as this is over, they are starting with another one. They are, let's say, very, very, very hard-working and very efficient, and also very kind and accessible people, and really they deserve as much as, well, a little bit less than Fernanda, but almost as much as Fernanda, our support. And my final comment before going into the specific subject is that next year we have the 13th International Symposium on Generalized Convexity and Monotonicity in Arequipa, Peru, July 24, 2020. For all of you who have any connection to convexity and to monotonicity, because we have a very, very, let's say, comprehensive concept of generalized convexity or monotonicity. So if your talk just has the word convex or monotone, you can go there. And it's a very interesting place, and I can assure you that it will be a generally monotonic and monotone meeting. So if you like monotone meetings, please go to Arequipa. Okay, go. So now I will go into the specifics. This is joint work with Felipe Lara, who perhaps is sitting around here, but I have rearranged so he is the co-author of all the papers and the main co-author, which I will mention, but the presentation is mine. So if there are some errors, they are mine, not of the, yeah. So, just a minute. Okay. So I will start with an introduction to asymptotic analysis. And then I will give 3 examples where we have obtained some new results or some contributions to the subject. First, I will speak about optimization and equilibrium problem in Banach spaces, then on mixed variational inequalities, and finally on second-order asymptotic functions. Okay. Now, the notion of asymptotic or recession directions of an unbounded convex set was introduced almost 100 years ago, but let's say that was just sort of occasional. And it was already discovered in the 1950s in connection with some applications to economics, and perhaps Wilfredo Sosa knows a little bit about that origin. No. Sorry. Okay. Now, in the 60s, Fenchel, let's say, started again with the study of asymptotic direction, And then the concept was extended later on to non-convex sets and also to infinite dimensional spaces. Poof. Something is wrong in the way I'm pressing this button. Okay, the most important advances in the convex case were presented by Rockefeller in his book, Convex Analysis. And for the non-convex case, we mentioned the developments by Luke and Penot in 2001. Well, now, a related notion motivated by the optimization problem is the concept of asymptotic function. Well, the analysis of the behavior of this asymptotic function, which I will define in a minute, associated to the objective function of a constrained optimization problem along the asymptotic directions of the feasible set, well, turned out to be useful for establishing existence of solutions and compactness of a solution set. As you know, in general, it is existent result are sort of hard and not very abundant. So the fact that these asymptotic directions give some hints on existence of solutions and also, in fact, compactness of the solution set, well, made them quite interesting. People like that. Oh. Okay. And they turn out to be a valuable tool in continuous optimization, variation inequalities, and equilibrium problems, particularly in the non-smooth case, because they do not require any differentiability assumptions. That is probably its main virtue as compared to other existence results. So now I will start to be formal. What am I doing here? Why is it that other speakers did not get into this problem? Okay. Given a non-empty set K, well, this is the definition of the recession cone. Most of you are familiar with it, especially those who have gone through Rockefeller's book. It's the set of directions such that you have a sequence in the set itself and the sequence of numbers, real numbers tk, will go to infinity, so that xk over tk approach u. So you can say that this is the set of directions through which you can approach, or which can be approached coming from points in the convex set. Okay. When K is a closed convex set, we have just that this K infinity, the recession cone, is just the set of directions of half-lines which start at any point in the set and are contained in the set. And in fact, the origin is irrelevant, because if you have a direction in the recession cone, you translate the half-line to any other point in the set as origin of half-line, and you are still in the recession cone. So now, what is the asymptotic function? Well, I start with a proper function, f, with n variables, with values in the extended real numbers, and the function, which I call f infinity, is such that its epigraph is the recession cone of the epigraph of f. Okay, and the epigraph of f is written there, but it's whatever is over the graph. So we have the recession cone and also the asymptotic function of a function. Que é o que estou fazendo?
Esse botão aqui não, aperta esse daqui.
Ah, isso, eu estava apertando o botão errado. Bem. So we have that definition of f infinity is the infimum of the limit of f of xk over tk, where xk is in the domain of f, tk goes to infinity, and xk over tk goes to u. So you think that the asymptotic function is defined on directions. Okay, you can vectors are direction, but it's better to think of as direction. Now, when f is convex, then it turns out to be that the f infinity is like the limit of the incremental quotient when t goes to infinity. You see that if I put t going to 0, that's the derivative. Well, this is like, so we call this a derivative at infinity. The idea is that this is more or less that thing. And since f is convex, you can write the supremum instead of the limit. And also you can write it as saying that f infinity of u is the supremum over all x in the domain of f of x plus u minus f of x. You see that here the function of u is like a, well, you can think that f infinity of u is that the directional derivative of f at infinity in the direction u. That's why I'm saying that it's better to think of u as a direction. Well, in view of the results, then f infinity can be seen as the directional derivative at infinity. Now I recall the notion of coerciveness. So a coercive function is a function such that goes to infinity when you move away from any wall, let's say when the norm of the argument goes to infinity. Now, and here we come to the classical result connecting asymptotic functions and existence of optimization problems, because, and this result is the one that we will try to extend to several other contexts, because this is, so, if the function is coercive, then this is just one implication. The asymptotic function is greater than 0 for all non-zero u. In all directions, it gets. Now, this is just one implication. Coerciveness implies positiveness of the asymptotic function. But in the convex and lower semi-continuous case, we have that f is coercive if and only if, what was written above, the asymptotic function is non-negative for all direction, non-zero direction, 0 is not a direction, if and only if, and this is the part that we want to emphasize, the set of minimizers of f is non-empty and compact. So, if you get to compute the f infinity, you will be able to make statements and categoric statements about the non-emptiness and compactness of the set of minimizers of f. So this is like our main, we will be extending this in several other courses. Up to this is very, very classic, and it's like more than 40 years old, let's say. This is no novelty. Now, if the function is non-convex, I mean, when I say we're trying to extend, we'll have to change the definitions, because the way I just wrote the definition of asymptotic function, if I move away from the convex case, it doesn't work. Suppose that, for instance, the function is quasi-convex, and even with coerciveness, the previous result fails. For instance, you consider the quasi-convex, continuous, and coercive function square root of the absolute value of x, which is something like this. Well, this function is, well, it's a very nice function, continuous, but it turns out to be the case that the f infinity, the asymptotic function, is 0 everywhere. However, f has a non-empty and compact set of minimizers, exactly just one point. The point is that in this case, in somehow the the F infinity will, like the way it was defined, will look at the, let's say, convex hull of that epigraph. So it looks as its function were exactly identical to 0, which is not the case. In that case, the set of minimizers is not compact. So I have to play a little bit with the definition of asymptotic function if I want to have a result like before for the case of, for instance, quasi-convex. Okay. And so a lot of people have been proposing alternative definitions. And it seems to be that, well, one of the most adequate, or here I more category, the most adequate is the Q asymptotic function introduced by Flores-Bazin. Flores-Bazin, his son, no, isn't it? Brother, yeah. Fabian Flores-Bazin, his brother, who is, well, I don't know, and Vera in 2015. There are other options, but I will stay with this one. And then what I will do is change a little bit, and I will say that F infinity Q of U is the supremum of F, the incremental quotient, like a derivative direction in the, as before, but then I'm taking not only the supremum over t greater than 0, but also on x's on the domain. Before that was not necessary because in the convex case I was saying in asymptotic direction no matter where you start. Here it matters, so I put one more supremum. And with one more supremum, things improve. And now I present the extension of the classical result with FQ. So it's almost the same as before. So now, if the function now is proper Lorentz and quasi-convex, then, okay, the Q asymptotic function is positive for all non-zero direction if and only if the set of minimizers is non-empty and compact. So I am more or less, I got something almost as good as I had before for the compact case. So, well, this is one thing. Now, I will start to deal with results which have been obtained in co-authorship with Felipe Lara. And the first thing we do is to consider the case of quasi-convex optimization in Banach spaces. The results look pretty similar, but they are considerably more complicated to establish. And then, the main problem, of course, is that we will have to deal with weak conversions because of the setting and not with strong conversions. We could use strong conversions. Things would be rather trivial, but it's not the case. So again, given a weakly closed set K, the asymptotic cone is the same as before. I mean, the definition of asymptotic cone is the same as before, but now almost the same, because now U is the set of weak limit points of vectors of the form tk xk, where xk is in the set and tk goes to 0. So now what I have is weak conversions. Okay. And then, well, first I present some basic results on the asymptotic cone, which are the same as in finite dimension. It is monotone with respect to inclusion. It is invariant by translations. The intersection, the asymptotic cone intersection is contained in the intersection of asymptotic cones. And if the intersection are non-empty and each one is closed and convex, then there is equality. Well, so now I define F infinity and Q infinity, I mean the asymptotic function and the Q asymptotic function, before the same as we did in the Euclidean case, and we consider the problem of minimizer f on the Banach space B. And then we, in order to get our theorem, I will invoke our theorem, two results from a paper of Atuch et al. And others. Well, first of all, one implication. F proper, if f is bounded from below, then the asymptotic function, classical asymptotic function, is non-negative for all u. This is sort of trivial, infinite dimension, not so here. Another result, consider the a weakly lower subcontinuum f. So if tk goes to infinity and vk goes weakly to v, and f of tk vk is bounded from above, then vk minus vk goes strongly to v. Okay. So this is a connection between weak and strong convergence. This is the first assumption. The second assumption is that the infinity, the asymptotic function is non-negative. And the third assumption is for every u such that every direction where the asymptotic function takes the value 0, we can move in the direction u a little bit, perhaps t, from x, and the function has not increases. With all these properties, then f has minimizers on B. This is not exactly what we would like, but let's say this is our departing point. Now, when B is finite dimension, the first condition is, the P0, which is the relation between, that some weak convexity implies a strong convexity is trivially satisfied. Same happens with f is coercive. And now we present our results. And it says the following, because now we will use the FQ, not the F. The previous result was not so satisfactory because at Touche we're using the F infinity, the classical one. Now I will use the new one. So B is a reflexive Banach space. F is a proper weakly lower subcontinuum quasi-convex, and an for convexity. If that P0 holds, which is the one saying that if I have, that some form of weak convergence and something else implies strong convergence for that sequence, then the set of minimizers of F is non-empty and weakly compact if and only if the Q asymptotic function is strictly positive for all non-trivial directions. So I recover more or less the same as in finite dimension, with the exception that I have to add that P0 property, which is, as I tell you, if I have a sequence which converges weakly to B, and I have a sequence of real numbers going to infinity, but f of tkvk is bounded from above, then the convergence is strong, not weak. Well, that's an assumption. But that's okay. Now I will introduce, because now I want to move to equilibrium problems. Equilibrium problems are defined in terms of bifunctions, functions of two variables, and so I want to have a Q asymptotic bifunction. And with this, I will get convergence results for pseudo-monotone operators and not for monotone. In the case of monotone, pseudo-monotone bifunctions. For monotone bifunction, probably I can do with the classical, with F infinity of Q. So first, I will define the equilibrium problem, which, given the bifunction F, I have defined on a set K, subset of the Banach space. I have to find an X bar such that X bar F of X bar Y is non-negative for all Y in the feasible set, or in the domain. Now, I will define the Q infinity Q asymptotic function given an F, bifunction F. The Q asymptotic bifunction is like that. I take F of Y plus TU. So I fix the first argument, and the second is the one I mean, I start at the point y, let's say, and move only the second argument in direction u, and take the supremum over t and the supremum over y, same as I did for function of one variable. It's a little bit like moving from f of xy to f of yy, but then when I move in the direction, I move only in the second argument, not in the first. Okay, well, that is and it is immediate that that function is positively homogeneous of degree 1. It takes the value 0 at 0. And if I have the case where f of yx is equal to h of x minus h of y, then I recover the scalar Q asymptotic function. That is, I get that the Q infinity by function is the Q infinity, I mean, is the Q asymptotic function of H. Because, and when I have an equilibrium problem with my function which is of the form h of x minus h of y, the equilibrium problem is equivalent to minimizing h. So this is reasonable. And then we get, in the second condition, without any monotonicity, convexity, continuity, assumption of f. If f is bounded from below, then the Q asymptotic function of the bifunction f is non-negative for all directions. Now we assume, make some standard assumption of the equilibrium problem. It is the bifunction is 0 on the diagonal, weakly lower semicontinuum, and quasi-convex in the second argument. It is pseudo-monotone, meaning that if f of xy is non-negative, f of yx is non-positive. Then we have F3 is like the same P0 before. It is a property which links weak to strong convexity. And finally, in the first argument, I just ask weak upper semicontinuity. And our second result, which is also in that paper used in Lara 2020, meaning that it's been accepted or not yet published, we get a result whose finite dimensional counterpart is in a paper published this year. Well, with all these assumptions I had before, if the bifunction, if the Q asymptotic bifunction is positive for all non-trivial direction, then again the equilibrium problem has a non-empty and weakly compact solution set. Now I move to another area. I go back to finite dimension, and I will talk about something which is called mixed variation equalities. Well, first, the variation equality when an operator T from Rn to Rn and a feasible set K in Rn consists of finding an x bar in the feasible set such that the image T of x bar makes a acute, or let's say non-obtuse angle with any direction starting at the point x bar and pointing to the feasible set. When T is the gradient of a convex function, then the variation equality problem reduces to the problem of minimizing G on the convex set K. But now I will consider a mixture. That's the mixed one. I have a T and an H. And I want Th of x bar, y minus x bar, I mean, plus h of y minus h of x bar, non-negative for all y and q. So it's like I have, for instance, if I had a solution of the variation equality problem for T, which is also a minimizer of h, okay, that's a solution, but in general, that of course doesn't happen. So when T is 0, that reduces the variation equality problem. With h is 0, reduces the problem of minimizing h. And, well, when T is affine, it takes that particular form, and I will mention later on a result for a affine function. That's nothing special, just I took T affine. And the solution set will be denoted as S of TKH. And now a little bit on existence of solutions, let's say, for mixed variation equalities. In the optimization case, if T is is identically 0, we know that continuity of H and compactness of K ensure existing minimizers, so solutions of this problem. Now, for classical variation inequalities, now with H identically 0, a consequence of our fixed point theorem implies that continuity of T together with compactness and convexity of K ensure existing solutions. This is also sort of classical. Now, one could think, okay, if I now have the mixed one, and I have that T is continuous, H is continuous, and K is convex and compact, well, perhaps I also have existence. No. So, there are simple counterexamples. For instance, this is more family of counterexamples. Suppose that T is strictly monotone when T of 0 equals 0. Suppose that K is equal to minus K, for instance, a circle, and that H of X is minus H of minus X. And I have some Y such that H of Y is less than H of 0. With any T, K, and H, we satisfy these conditions. It's very easy to find a lot of functions. To find this, the mixed variation inequality problem has no solution at all. So, and this T, K, and H can be very, very nice. T can be the identity, K can be a ball, and H can be a linear function, for instance, and it doesn't work. Well, that was the example. H is the square of the norm, K is the ball, and T is the identity. Therefore, some further assumption on H is needed, even for convex and compact K. One such assumption is convexity. One in 2017 proved that if the variation inequality problem H is lower semicontinuous and convex, T is upper semicontinuous, and K is compact and convex, we have solutions. Okay. We can also invoke results for equilibrium problems, and well, that's another possibility. But here, we'll establish a commercial result covering instances which do not fit either 1 2017 or Iusem Lara 2019A, which was writing the using equilibrium problem results. And we will use H infinity instead of F infinity. And we need a property introducing 1, 2017. A pair TH has the mixed variation equality property if it has solutions for every compact and convex subset D. So we are assuming that in the compact case we have solutions, which might not be the case, as we said before, and we want to establish solutions with for K, not for D. D is in compact subsets of K we have solutions. What about solutions in K? Well, here we have a family of problems which satisfy this property, and we have, for instance, take a lower semicontinuous H, closed and convex K, a cone P, and T is K copositive, that is copositive with respect to K, continuous positively homogeneous on degree 1. The image of K is contained in a dual cone, and the function H of X plus T of XZ is quasi-convex. Then, for instance, those have this condition, those functions. So this will give me examples where the previous assumptions do not hold. Okay, so now the theorem, H lower semicontinuous, nothing about convexity. K closed and convex, T is K copositive, continuous are positively homogeneous on degree 1, and the pair TH has the MV property. So when I take a bounded subset, or that is a compact subset of K, I have solutions. So now, if there exists X bar such that the infinity, that the asymptotic function of H at U minus TU X bar is positive for all U in the recession of cone of K, then the set of solutions is non-empty and compact. And of course, the result is meaningful only when k is unbounded, but because the bounded case, I'm putting that in the assumption. And we have a corollary for the affine case. That's okay. And well, now there is an example for which our result holds and the previous one do not. T is just separable with T1 up to T, not separable. It's separable, really. T, I write it as T1 up to T, and Ti of x is just the maximum between 0 and xi, component-wise. H is that thing which is there. The square of the norm, if all the inside the ball and the minimum between 1 and the square of the norm 1, otherwise, and I take a closed and convex set K, which does not contain the canonical basis, and which is contained neither in the negative ortho nor in the positive, and T is neither affine nor coercive, H is lower semi-continuous, but is neither convex nor coercive, so I am not within the previously known cases, but T is continuous particular homogeneous of degree 1 and copositive, and it can be proved that it has the MVIP property, and there exists such x hat, in fact, that the inequality holds for any x, that inequality, and hence our existing result proves that the mixed inequality, mixed variation inequality has the set solution on empty and compact. And finally, I will address a problem, second order asymptotics. The idea was that okay, as I was saying before, if I have a convex but non-coercive f, the asymptotic function may fail to provide useful information from the behavior of f on the behavior of f at infinity. For instance, if we take minus log, then the asymptotic function is identically 0, and I know nothing about the fact, for instance, that f goes to infinity. In order to deal with that situation, Luke and Hadji-Savas in 2011 introduced a second order asymptotic cone. And so, if I have the set K, I have one direction. Now, another direction V is to be a second order asymptotic direction of K at U if there exist cone sequences xk in K and sk and tk in R, sk and tk going to infinity, such that V is the limit of that expression, sk over sk minus tku. The set of such direction is the closed cone K infinity 2, called second order asymptotic cone. It is non-empty when U is in the asymptotic cone, and K infinity 2 of 0 is just K infinity. And then, in Flores, Bassam, Hadji-Savas, and Lara in 2015, a second order asymptotic function was defined, and given an f, and the U in the domain of f infinity, the second order asymptotic function of f at U, but which is a function of another variable b, is the function whose such that its epigraph is the second order cone of the epigraph evaluated at the point U, f infinity of U. Well, this is like a second order asymptotic function. And, well, it has those properties there. And when f is convex and x in the relative interior dominion, I have a nice formula, and it's like this. The f infinity 2 is the supremum on S, infimum on T of x plus Tu plus SV minus T f infinity of U minus f of x divided by S. Or if you want, I can replace those by limits. double limit of the same expression. But these equalities do not hold when f is just quasi-convex, which led to the following modification introduced by Flores-Bazan, and Lara, 2016. And now I add to all this a supremum on x in the domain of f. So supremum over s, inferior 2, and supremum over x, which is the fq. And with this definition, the desired equalities do hold for a quasi-convex f, and it's the same trick that we did before to move from the f infinity to the fq infinity. Add a supremum over x. But still, this definition works for other purposes, but I don't have information on the convexity or concavity of the original function at infinity. And if the asymptotic function gave me that information for as a derivative, let's say, now the second order asymptotic function should give some information on the convexity. And for that, I give another definition. And now it goes like this. F of x plus h u plus v. So I increment in the direction of plus v minus increment in u minus increment in v plus f of x divided by h squared, which is like the approximation as a quotient of the second derivative. This is the idea. But now I don't take the limit when h goes to, the quotient is the same as the approximation, but I'm not taking the limit when h goes to 0, but with h, when h goes to infinity. And now, one question, and we call it f infinity infinity instead of f infinity 2. We are running out of indices and sub-indices for these things. One thing which would be interesting to know is in what cases that does not depend on x. And what we prove is that the lower semi-continuous function with convex domain, in fact, it does not depend on x. So you can just take the limit in h. And for quadratic functions, yeah, we get the information. When I take that quadratic, I can compute. And the f infinity infinity at x direction uv is u transpose ab. But of course, u transpose ab, whether it is positive or negative or so, will give me this information. And well, this infinity infinity has some properties, it's symmetric. At u0, at 0v is 0. If the domain is just, if the domain of the, if the recession cone of the domain is just 0, the double infinity function is identically 0, is simultaneous positively homogeneous a function of u and b, and you have that like a triangular coin. U w plus z equal u plus z w plus uz minus zw, and the h infinity of the sum is the sum of h infinities. And if f belongs to phi, and this phi was well, it is the functions for which that does not depend on x, which includes the lower semi-continuous convex domain, but then f infinity infinity of u gives me the convexity or concavity of the function f at infinity. And it is different from f infinity 2 and from f infinity 2 sub q. And also it makes it possible to obtain interesting results both in quadratic and fractional quadratic programming, and this is the end. And so something about Attouch, Boutage, Michaele, Bloom, Etli, Flores-Bazan, Vera, Flores-Bazan, and then finally my papers, recent papers with Felipe, Kinderle Stampaya, and Luc Benot. So that's all. Thank you very much.